Hello everyone, I am Li Qina from the Electronics and Information Engineering Teaching and Research section at Wuzhou University and welcome you to this mini lecture. Today we'll cover section 6.3, the inverse Laplace transform for continuous time signals. Earlier, we derived the general formula for the inverse Laplace transform for a continuous time signal, which is shown as follows. If the Laplace transform maps a signal from the time domain to the complex frequency domain, then the inverse Laplace transform restores the signal back from the complex frequency domain to the time domain. In practice, there are two main approaches to computing inverse Laplace transforms. 1. Using the residue theorem from complex analysis. 2. Applying the method of partial fraction expansion. In this lecture, we will focus on computing inverse Laplace transforms through partial fraction expansion. In the examples provided, we are given three Laplace transform expressions, Fs, corresponding to different signals. The task is to use partial fraction expansion to find their inverse Laplace transforms. Through these three examples, we will illustrate the three common forms of partial fraction expansion. The core idea of using partial fraction expansion to compute an inverse Laplace transform is to expand Fs into a sum of partial fractions. Each fraction in the S domain can then be converted into its corresponding time domain expression, and by summing them all, we obtain the signal Ft. Typically, Fs is a rational function expressed as follows. The numerator polynomial Ns and denominator polynomial ds can be factored into first, or higher-order terms. The roots of ns equals 0 are called zeros, while the roots of ds equals 0 are called poles. The first case of partial fraction expansion is when fs is a proper rational function, meaning the degree of a numerator polynomial is lower than that of a denominator polynomial, and all poles are simple first-order poles. In this case, Fs can be decomposed as shown in the formula. Here, the denominator polynomial ds is expressed as the product of several first-order factors. Fs is then expanded into a sum of partial fractions, each with a denominator equal to one of the original first-order factors of Fs. The numerators, denoted as kn, are unknown constants to be determined. Each constant ki can be solved using the given formula by substituting the corresponding pole value into S. Finally, each partial fraction in the S domain is converted into its corresponding time domain expression. By summing them all, we arrive at the expression of the signal Ft. After learning the first form of partial fraction expansion, let's return to the first example, Fs, given in the exercise. By examining this expression, we can see that Fs is a proper rational function. Its denominator can be factored into the product of three first-order terms, and all the poles are simple first-order. Therefore, this fraction falls under the first form of partial fraction expansion. We can now apply the corresponding procedure to compute its inverse Laplace transform. First, expand Fs into the sum of three partial fractions. Each denominator corresponds to one of the first-order factors in the original denominator of Fs, while the numerators, denoted k1, k2, and k3 are unknown constants. Next, calculate the values of k1, k2, and k3 using the appropriate formula, where S is substituted with the value of the pole corresponding to each fraction. Finally, convert the three partial fractions in the S domain into their corresponding time domain expressions by referring to standard Laplace transform pairs. By summing them together, we obtain the expression for the signal Ft, as shown in the formula below. The second form of partial fraction expansion applies when Fs is a proper rational function and has poles of multiplicity r, i.e., repeated poles. In this case, Fs can be decomposed as shown in the formula. Here, the denominator polynomial ds is expressed as the product of first-order factors and higher-order factors of order r. When expanding Fs into partial fractions, each denominator corresponds to either a first-order factor or a repeated factor of order r. The repeated factor is further decomposed into a series of fractions with denominators of first, second, third, up to our order. The numerators, denoted by kn, are unknown constants to be determined. If the denominator corresponds to an order repeated pole, the coefficients kj can be calculated successively using the given formula, whereas is substituted with the repeated pole value. If the denominator corresponds to a simple pole, then the coefficient ki is calculated in the same way as in the first form of partial fraction expansion. Finally, each partial fraction in the S domain is converted into its corresponding time domain expression, and by summing them all, we obtain the complete expression for the signal ft. Let us now return to the second example, fs, given in the exercise. By examining this fraction, we can see that fs is a proper rational function. Its denominator can be factored into the product of a first-order term and a third-order term. Accordingly, the poles consist of one simple pole and one pole of multiplicity 3. Therefore, this fraction falls under the second form of partial fraction expansion. We can now apply the corresponding procedure to compute its inverse Laplace transform. First, expand fs into the sum of 4 partial fractions. The denominator of the first fraction is the first-order factor s. The denominators of the remaining 3 fractions are the terms arising from the third-order factor, s plus 1, s plus 1 squared, and s plus 1 cubed. The numerators of all 4 fractions are unknown constants. Next, calculate the values of these constants k1, k4, k3, and k2 using the appropriate formulas. Finally, convert each of the 4 partial fractions in the S domain into their corresponding time domain expressions by referring to standard Laplace transform pairs or properties. By summing them all, we obtain the complete expression of the signal ft, as shown in the formula below. The third form of partial fraction expansion applies when fs is an improper rational function, meaning the degree of the numerator polynomial is higher than that of the denominator polynomial. In this case, fs must first be separated into 2 parts, a proper rational fraction and a polynomial, as shown in the formula. The proper rational fraction is then handled using either the first or second form of partial fraction expansion, depending on the nature of the poles. The polynomial part in the S domain corresponds, in the time domain, to impulse functions and their higher-order derivatives. The corresponding forms are shown in the formula. Finally, by adding together the time domain expressions obtained from the proper rational fraction and from the polynomial part, we obtain the complete expression of the signal ft. Now let us return to the third example, fs given in the exercise. By examining this fraction, we find that fs is an improper rational function, and therefore it falls under the third form of partial fraction expansion. First, decompose fs into 2 parts, a proper rational fraction and a polynomial, as shown in the formula. The polynomial part in the S domain corresponds to impulse functions and their higher-order derivatives in the time domain. The denominator of a proper rational fraction has 2 simple poles. Therefore, the first form of partial fraction expansion is applied to compute its inverse Laplace transform. Finally, by adding together the time domain expressions obtained from both the polynomial part and the proper rational fraction, we arrive at the complete expression of the signal ft, as shown in the formula below. Now, let us conclude today's lecture on the inverse Laplace transform for continuous time signals. When using partial fraction expansion, there are 3 main forms to consider. 1. Fs is a proper rational function with only simple poles. 2. Fs is a proper rational function with poles of multiplicity r. 3. Fs is an improper rational function, which must first be decomposed into a proper rational fraction and a polynomial. It is essential to master the methods for computing the inverse Laplace transform corresponding to each of these 3 forms. Please reflect on today's lecture and complete the following homework exercises to consolidate the concepts learned and deepen your understanding. That concludes today's mini lecture. See you next time.